dual credit, we're going to look at falling objects. So Galileo is a scientist, and Galileo as a scientist looked at objects falling. And based on the work that he discovered, is he claimed that all objects that fall, no matter how big, how small, if you take air resistance out of the equation, that they would all fall at the same constant acceleration. So, for example, if we had an air-filled tube and we dropped a feather in a rock, the rock definitely would fall farther, would fall faster, because the feather would have more air resistance. But if we took all the air out of the tube, they would fall at the same rate. Sheet of paper and a ball. The sheet of paper floats down while the ball drops. If you crumple the paper up to the same shape as the ball and drop them, we would see a lot closer, if not the same. Again, without air resistance, things will fall at the same rate. And that rate on Earth is 9.8 meters per second squared. So that's the acceleration due to gravity, 9.8 meters per second squared. In the absence of air resistance. Don't forget that in the equation. So, let's say we have a ball dropped from a tower 70 meters high. How far was the ball falling after 1 second, 2 seconds, 3 seconds, etc.? So, our initial velocity is 0 because we're dropping it. Okay? So, our initial velocity is 0. Up here, we'll say, is our initial position is 0. The bottom is our final position. Now, we're going downward. So we're going to make our final position negative 70 meters, because that's how far we're dropping from 0. And because acceleration due to gravity is 9.8, and it's pointed in the downward direction, we're going to call it negative 9.8. So what we're trying to find is, right, how far it's going to fall after 1 second, 2 seconds, 3 seconds, etc. Drawing all of this down, here's what we could do. Okay, we got velocity final. We don't know, right? So we can't use that equation. So we got to start thinking about which equation will work the best for us at our different times. I'm going to say that we want to find our final position. Okay, when our initial position is 0, our initial velocity times time plus 1/2 at squared. Okay, so we're trying to solve for x. Since our initial velocity is 0, we get rid of this. Initial position 0. It's going to be 1/2 at squared minus 9.8. And since t is going to be 1 to start, we're going to put 1 there and we're going to square it. And when we do this math, for 1 second, we're going to find out it's going to be 4.90 meters. Now to find it for the other times, okay, the 2 and the 3, I keep everything the same except my t. So t squared is 4, so I'm going to take negative 4.9 times 4, okay, or 4.9 times 4, which would be negative 4.9 times 4, and what I'll find that to be will be 19.6 meters, negative. And after 3 seconds, negative 44.1 meters. Okay, and this is using that equation. Again, if that's 0, that'll be negative going down. That's how we work that problem. Keep track of your signs. Now suppose the example, the ball's throwing downward with initial velocity of 3 meters per second instead of being dropped. Alright? So what would be its position after 1 second and 2 seconds? I like looking at that and saying, okay, so we got our same 70 meter tall drop, but now our initial velocity is 3 meters per second. Our time is still going to be 1 second and 2 seconds. Our initial position is still going to be 0, and acceleration is still going to be negative 9.8. So how does changing the initial velocity change our distance? Well, let's take a look. So initial position is still 0, but now our initial velocity is going to be 3. Our time is 1 second, and then we go 1/2 negative 9.8 times 1 squared. Now let's think back about our velocity. If we're throwing downward, our velocity is also going to be negative, so that's going to be negative 3 times 1. So x is going to give us negative 3, and we do all that out, and we get a distance of negative 7.90 meters. If I substitute 2 seconds, and for this, and again, go through all the math, I get negative 25.6 meters. So by giving it an initial velocity, we've changed the distance. I mean, the distance went from negative 4.9 to negative 7.9, and that's just adding the initial velocity to it to get that distance there. So that initial velocity does cause something to happen. Now, what would its speed be after 1 second and 2 seconds? Well, final velocity is equal to our initial velocity, which is negative 3, plus our acceleration of negative 9.8 times time, so 1. So this would be negative 12.8 meters per second. And after 2 seconds, it would be 19.6, 22.6 meters per second. But that's how you can find the final velocity. Now, let's go back and say instead of throwing it downward, we're going to throw it upward, 15.0 meters per second. Now, upward's positive, so now we're going to have a positive initial velocity. Same equation. And so we're going to calculate how high it goes and how long the ball's in the air before it comes back to his hand. So we're throwing it up here, all right? So how high it goes, x equals x of naught plus VOT plus 1/2 AT squared. There's a problem with using that equation again, right? We don't know time. So which equation does not have time? Well, as most of you figured out, we could use this equation. Okay, so our final velocity, and we want to say how high it goes. Let's think about what happens when we throw it high. When we throw it straight up, when it gets to the top, what's its velocity? It's going to be 0. So how high the ball goes is when our final velocity is 0. Initial velocity, 15 squared, plus 2 times negative 9.8, because our acceleration is negative. And that will be our change in x. So for our velocity to go from 15 to 0, and we'll do the math and we'll see what we get. So we get 15 squared is 225. We divide that by 2 times 9.8, and we get a change in x of 11.5 meters. So the max height is going to be 11.5 meters. Then it comes back down. So the question is, how long is the ball in the air before it comes back to his hand? So it's going all the way up 11.5 meters and coming all the way back down. And we want to solve for t. So we can again go back to this equation now that we didn't go to before, and we can solve. Okay, we know that our initial position and final positions are both going to be 0, right? That's 0 and this 0 because we're starting and finishing at the same spot. So our displacement's 0. Our initial velocity is 15 t plus 1/2 negative. I'm going to write this down somewhere else right here. So we got 0 is equal to 15t minus or plus 1/2 negative 9.8 t squared. And to solve this mathematically, we can factor the t out, and we get two options. We get t is equal to 0, or t will be equal to 15 over 4.9. And that's going to be our answer. It's going to be 3.06 seconds. So we just solve for t in that equation to find how long the ball's in the air before it comes back to the hand. Now, let's talk about misconceptions. Acceleration and velocity are always in the same direction. Obviously not true, because in the case in this picture, when we throw a ball up, velocity is going upward, but gravity's pulling us down. So that's not going to be the same direction, especially on the way up. When an object is thrown upward, it has 0 acceleration at the highest point. Gravity never changes. My acceleration of g of negative 9.8 is constant throughout the traveling of this ball. So it's going to be the same from the top to the bottom, okay? It's going to start out at negative 9.8, all the way at the apex of the height, where velocity is 0. It's still going to be negative 9.8, but acceleration never changes. Now let's consider again the ball thrown upward in that example and make more calculations. How much time it takes for the ball to reach the maximum height. Okay, so let's go back and take a look at that. Okay, so we got 15 meters per second, and we want to throw that bad boy up in the air, and we want to see how long it takes to get to its max height. So let's look here, and how long it gets to get to the max height, right? And so we know our initial velocity, final velocity plus AT, because we want to solve for time. Our final velocity is going to be 0. Our initial velocity is 15. Our acceleration is negative 9.8, and t is our time. And again, algebra, we solve for t, and we get t to be 1.53 seconds. So it takes about 1.5 seconds for it to reach its max height. What's the velocity of the ball when it returns to your hand? Now this is really a thinking question, but let's do the math to prove it here. Okay, same equation. Let's say we want final velocity equal to initial velocity plus AT. Okay, we know, and I think we figured this out to be 3.06 seconds here, right? So to go from up to back to our hand. So our final velocity we're solving for, our initial velocity is 15, our acceleration is negative 9.8, and our time is 3.06. And so we plug those numbers in and we chug them out, and our final velocity is going to be negative 15 meters per second. So here's something you can pick up. If I throw it upward at 15, when it comes right back down to my hand, it's going to be going the same velocity, because our acceleration is constant. It's going to be going the same velocity when it comes back to my hand, just in the other direction, or the negative direction. Last thing to look at is a ball being thrown upward again. Okay, and we want to take a look at the same example in 14. What time the ball 8 meters above the person's hand? So we want to find what time t the ball passes a point 8 meters above the person's hand. So we're going to come out with the same equation: initial position plus VOT plus 1/2 AT squared. And we know that our final position will be 8 meters. Okay, our initial position will be 0. Initial velocity is 15t plus 1/2 negative 9.8 t squared. What you're going to end up finding is that we're going to have a quadratic here, and we're going to bring all this over, okay? And our quadratic's going to be 4.9 t squared minus 15t plus 8 equals 0. Use your calculator to solve the quadratic equation. Don't go into the whole big process mathematically. You can if you want to, but you're going to get 2 t's in the end. The first t is going to be 0.69 seconds, and the second t is going to be 2.37 seconds. Are both valid? And the answer is yes. Think about this, because it's going to leave your hand and it's going to come back down, right? So when it gets to the 8 meter point above your head, it takes 0.69 seconds. For it to go to the apex and back down again to be 8 meters away is 2.37 seconds. So both answers are right. The first answer is on the way up. The second answer is on the way down. Quadratics will come up with these.